Hello, welcome to Data Science with EJD. In the previous video, we started looking at regression algorithms in supervised learning, in machine learning, if you like. Now we're going for polynomial regression because we know that sometimes linear regression has some limitations because it may not capture non-linearities in data sets. So let's go for polynomial regression. And when you talk about polynomial, it's anything from, linear regression is just the highest power of is one, right? But for polynomial regression, that you can have quadratic, cubic, quartic, and so on and so forth. So that's polynomial regression. So the learning objectives here are to understand polynomial regression and how it fits nonlinear curves, then learn how to fit polynomial models of varying degrees, then understand the concept of overfitting and underfitting. Then you want to analyze model performance on training and test data to detect overfitting. All right. So first thing, introduction to polynomial regression. Polynomial regression is a type of linear regression. So actually, polynomial regression is actually a type of linear regression. We can see it like that, where the relationship between the independent variable x and the dependent variable y is modeled as the nth degree, right? The relationship between the two are modeled at the nth degree instead of the first degree that we did for linear. So you now have something like y equals beta naught plus beta 1x plus beta 2x squared. So it's this same variable x now. You do for multiple regression, you be having like beta 1x 1, beta 2x 2. But here it's the same variable x, the same feature, but at different degrees, right? So up to the nth degree. And of course, that is associated with some kind of error. All right. So despite the polynomial terms, it remains linear in terms of the coefficient. So in terms of coefficients, we still have a linear regression, but that's why we say it's a type. So we still have, it remains linear in terms of the coefficient beta sub I, right? Is allowing the use of ordinary least squares for fitting. I think in the previous video we have done something like least square, trying to do that manually and seeing the actual maths. So why do we use polynomial regression, right? That we do that when data exhibits a curved or nonlinear trend. So sometimes when you get data, you may just want to plot the data and see how the behavior looks like. So that can give you some light into the kind of regression you want to carry out. So when data exhibits a curved or nonlinear trend, a simple linear model may not fit well. Then you have polynomial regression, allowing us to capture curvature and nonlinear patterns. So it's pretty much about the same idea. So overfitting and underfitting, key concepts. So one thing when you are doing working in machine learning with machine learning is the idea of underfitting and overfitting. So underfitting means probably the model you're using is too simple. If you use a linear model on highly nonlinear data sets, that can lead to underfitting. So that means there will be poor performance on both training and test data. And how do you measure that? You need to measure the performance of the training set and the performance of the test set. Then you have overfitting. In this case, it may be that the model is too complicated, too sophisticated for the data set you're working on. So here you have very high degree polynomial. So this fits noise in training data and performs well on training data, but poorly on unseen test data. So in this case, now if you do the metrics, you can see that the training data, the training set is very high, while the test set is very low. You know, that that in that case there's overfitting. So and sometimes it can be just right. In this case, you have a model complexity that balances both bias and variance and does good generalization. So it performs well on the training set and performs well also on the test set based on the metrics that we use. Then let's talk about data set selection and preprocessing. So here we will use the California housing data set to model how median house values vary with median income. That was the same data set I think we used when we're talking about linear regression, and we'll also be using this even after this video. I think in the next video we're talking about regularization. That's one way of dealing with the problem of overfitting. So regularization, talking about ridge and lasso regression. Okay, so so the usual thing is to want to load the data set and select relevant features. Of course, you have NumPy, Matplotlib, scikit-learn, and all the associated things like that. And then, so you want to load California housing data set. So just the data is fetch California housing. This is where we got it from. Okay, I think I want to get the line numbers. So for easy referencing, now that's in place. Okay, so we brought the data set, we fetched it at line 3. Now we are giving it a name, right? So that we can now use it in this place. So here we have to select the feature, median income and target. That's median house value, like that. So X data dot data 0 reshape. So this is median income. And for our target now, we need the median house value, right? So for clearer visualization, we can filter out extreme value. So we say we mask, say, while that's housing data now, less than 5. We are talking about linear regression. Okay, we're talking about polynomial regression, but it's one feature on one feature. So it means that here, the we are trying to predict the median house value based on the median income, and then we just want to pick. So want to filter out some values. So anywhere the median house income is less than 5, and whatever we selected is less than 10. So something between 5 and 10, that's what we're picking out. So we can, so by running this now, you can see, um, okay. So each time I do this, I guess I need, okay, nice. So here, if I can run this now, and that is done. Okay, it's still working. So now it's done. So we can now see what X looks like. So this is what X looks like. So these are so this is the median income, like that. And then for Y, now this is the uh median house price, like that. So it's just one on one, except that we now have this to whatever degree we want. So then we want to split into training and test sets. So that's the standard process right now. So here you have the X train, X test, Y train, Y test, train test split, X Y, random stage is 42. I think there's something, I think, yeah, test size. We usually have test size. Here, our test size is going to be 0.2, right? That's 20% for test, 80% for train. So test size is 0.2. We run this, that's done. Now, talking about polynomial regression modeling now. So, because it is polynomial, it starts from order 2. It can be quadratic, cubic, order 3, quartic, order 4, and so on and so forth. So degree 2 is quadratic model, which is moderately flexible after linear model. Then we have degree 4, which is higher, it has higher flexibility, potentially capturing more complexity, but risk of overfitting. So the higher the polynomial is, the more the risk of overfitting. So you have to be able to you want to try out different things and see which one gives you the most reliable kind of model for the data you're working with. Okay, so here you want to define function to fit polynomial model and evaluate. So here we are defining a Python function, right? So you have def that's defined, fit and evaluate polynomial. The name of the function is fit and evaluate polynomial. So it takes the degree, whether degree 2 or degree 4 or degree 3 or whatever degree, then the X train, the Y train, the X test, the Y test. It takes those values in and it fits polynomial regression of given degree. So whatever degree if specify it to give it to you, then it evaluates performance and returns train model and transformer. All right. So you want to transform input features to polynomial features. So poly transformer. So you need polynomial features of whatever degree. Then includes bias false. Then X train the polynomial. So you have polynomial underscore transformer dot fits transform X train. Then you have X test poly, that's poly transformer dot transform X test. Then you want to fit linear regression model and polynomial features. So you see, we said though it is polynomial regression, right? But it is still a type of linear regression. But the other things, the whole polynomial transformation thing we do is what makes it what it should be. So we now have model, we have linear regression, the model fit. Now, so you see the model fit is on X train poly and then the Y train, right? That's where the transformation takes place because the Y train is on its own, but the X train, right, has to be. So this what we have done here is to put it in polynomial form of whatever degree that is specified here. And then you now predict on train and test set. So X train pred model predicts X train poly, Y test spread model predicts X test poly, like that. Then you want to compute mean standard errors. That's to evaluate the model. And then so you have train MSE, test MSE. So this will tell you the performance of the train and test data set to see if there is overfitting, underfitting, or maybe it's just okay. All right. So we also want to, so you want to print these values, the degree of the polynomial regression and all that. So if you click on this, so everything now it's fine. Like we have done all the fitting and all the train sets and all that, but we now need to bring out those values now by calling that polynomial. So we can say fit second degree polynomial regression. So in this case now you just call this fit and evaluate polynomial. Now this is what you use to call what you need to call. So if you want to fit second degree polynomial regression, so you have model degree 2, poly degree 2, fit and evaluate model. So degree is 2, x train, y train, x test, y test. Then for degree 4, you also have all that now. So except that here it's now 4. So if you run this, you also get the values. For degree 2 polynomial, you see that the train mean squared error is 0.5382. The test is 0.5625. So very close. For degree 4, you have polynomial regression. Degree 4 polynomial regression rather. So the values are also close, except that yeah, they look pretty close in nature like that. So you may want to do other metrics to get to decide which of the two is actually better. So sometimes it can be a bit of issue reading out the mean squared error, except if you have very high, especially if you have very high values and all that, right? So, but I mean, from what we see that the performance on the train and test sets are about the same. So the model seems to fit well at this level, except if you want higher accuracy or something like that. So we can also visualize we can do visualization of fits and overfitting. So visualized fitting curves over the data allows intuitive understanding of underfitting and overfitting. So here what we just do is we create a range of x values for smooth curve plotting. So for the x range now, so you have x dot mean, x dot max, and you divide into 500 equal shapes and you reshape. Then you transform x for polynomial features. So x range polynomial of degree 2. So you have polynomial degree 2 transform x range polynomial of degree 4, polynomial of degree 4 dot transform x range. You know, we have defined all this above before, polynomial degree 2 and all that. Then you want to also have your predicted values over the range now. So y range pred degree 2, y range pred degree 4. So model underscore degree 2 predicts the range. 4 you also predict, and then you plot you do scatter plot for all the both train and test sets for both degrees, and then you also have the plots for you have the linear plots for the degree 2 fit and the degree 4 fit, something like line of best fits, and then the x label is median income while the y label is median house value. So because you're predicting median house value based on median income, all right, so we run this and then we have this nice plot right here. Okay, so you see the green lines are the test data. So the training data are the gray lines, right? The test data are the gray lines. The training sets are the gray lines, right? 80% of the data, and the test are the green ones. So you can see there's a nice performance. I mean, it's fairly nice, so to speak. And then we now have the degree 2 fit. The line of best fit is blue, whereas the degree 4 fit is red. All right. So, based on the performances, it's almost the performance is fairly about the same. So either of the two can do a good job on the data set we have. So let's talk about the interpretation and summary. So for degree 2 now, we have lower training error and reasonable test error. So in this case, we have uh, lower training error, right? So on 5382. Okay, I think these are not the basis for this. All right. So we have lower training error, so comparable training and test MSC. So the training and test MSC are about the same. So model fits main trend and good generalization. Then here we have very low training errors, possibly higher test MSC, depends on data sets. So I think we have fairly higher MSC values, right, for degree 4 from what we observed. So a bit, okay, that degree 4 values are a bit less than this. All right. You know, uh, it's reading MSE, right, can be quite, it can be a bit of challenge sometimes. So compared to R squared score, which is definite that the closer to one the better. So sometimes it can be tricky on reading the meaning of MSE. So model fits main trend. Okay, here model fits training data very closely, maybe overfitting. All right. So overfitting explains. So the 4-degree polynomial model has more parameters and can wiggle to fit the noise in training data, lowering training error. All right. So, however, this excessive complexity causes it to perform worse on new test data, showing higher test error. So this is overfitting, high variance support generalization. For the data we have here, right? You see, the performance on the test is even better than on the train. So, well, I mean, MSC, like I'm careful to interpret MSC because it can be a bit tricky. Maybe in subsequent videos I can give a clearer explanation of what how you should interpret MSC. But when you have something like R squared, the closer to one, the better. And there's the idea of underfitting. So a model with degree one, simple linear regression, would often have both high training and test errors when the data is non-linear, showing underfitting. So that's clear, right? So how to avoid overfitting? You can use simpler models when appropriate. Then you can use regularization techniques like ridge and lasso, which we'll be considering in the next video. Then you can use cross-validation to select model complexity and also increase training data size, right? So talking about optional extensions, you can try degree 1 linear and degree 10 polynomial fits to see extremes. So you want to try something linear and something of degree 10 to see what the extremes look like, and then that can help you make your decision. Then you can plot learning curves, that is the training and validation errors versus training set size. You can also use cross validation to select polynomial degree. We'll talk more deeply about some of these things in subsequent videos because I'll still be talking about regression metrics, just like we talked about classification metrics. And you also want to regularize polynomial regression using ridge or lasso. Interestingly, we're doing ridge and lasso in the next video. So this is just the full code summary. Everything we've done before, we are just putting it all together in one code. All right. So if you run this now, you just get everything in one blow. Okay. So run this and then you just get all the results you got before. So with this, we come to the end of this interesting video on polynomial regression, which we see as a type of linear regression, except that the degree is not one, it's two or more, right? So let me know how helpful this video is for you. And if there's something you'd like me to try out, feel free to let me know. If you have subscribed to the channel, thank you. If you haven't, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of the channel. There are 3 degrees of membership right now. There's silver, gold, and silver, bronze, silver, and gold accesses. So those will grant you some extra privileges, like maybe having consultation times with me or getting my PDF notes for the math courses the math topics I teach, and so on and so forth. And you can have a badge displayed beside your name also as a member of this channel. Then you can also have just some videos made for only members of the channel. All right. So uh feel free to do that and be sure to like and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.